Good morning, everyone.
Hey, Professor, quick question.
Yeah,
I
what's
wrote
up?
you an email about the Respondus practice test.
Yeah, I've
I
had
didn't
a
know if
couple
you
people
were
do
able
that.
to say again.
I've had a couple people do that. So this class is having the problem too, where it's getting like an error message when you click on it.
It says that the quiz is locked.
Well, it should be today because it was due like last night, I think. But
Yeah, I tried to do it, what was it, either yesterday or day before, and it said it had been locked. And my question to you, I saw that it was locked. I didn't know if you would unlock it to do it because
uh,
I thought I had done it, but I did it for a different class instead, so I wanted to make sure it was good.
yeah, I'll go ahead and open it back up. I think what I'll do is I'll make it due to Friday night by 11:59, maybe even Saturday night, and I'm going to open it up for all my classes. I just got to double check, see what's wrong because I got two different classes said they were getting error messages when they did it. So I don't know what the crap's going on.
Okay. And then just one other question unrelated to that. For the lab that's due today, what would
Uh-huh.
be an acceptable percentage error? Because I got one and I just want to make sure that it's, within your
This
tolerance.
is the one where you determine the mass of the electron. I think it was about 10 to 12%, somewhere around there.
Okay. All right. I just wanted to make sure I was in the ballpark.
Yeah, we didn't really have as much data as we'd really like to do that as properly. So it's good enough if you're getting within 10%.
Yeah, that's roughly what I got. Like I said, I just wanted to make sure I Googled, what's acceptable percent error in university physics, and it's like anywhere between 0 and 15%, but typically professors would be looking for around 5, and I was like, well, that's definitely not what I got.
Yeah, most of our labs we should get under 10, but like this one and a few others, sometimes it'll happen to be slightly over 10, and that's fine.
Okay.
I never want 20%. Probably if you get 20% or something like that, or 15% even, you probably made some kind of error in your analysis.
Okay. Yeah, I definitely didn't get that high.
No problem. And Krisha, I did see your email. I did not read it, but I did see it. I will address it immediately after class. Or you can talk to me after class, either one. Anybody else have any questions? I got a few examples. A couple of them are lengthy, and I'm trying to give you the sort of the worst case scenarios of problems so that you can be prepared for obviously the easier ones. But this is way beyond what's normally as an example in a textbook, say. So I'm going to give you a couple of examples like that. The very first one's just a very simple, straightforward example, but the other ones, like I said, I broke one problem up into 3 or 4 examples, and by doing that, I can just get one big problem that would not be unreasonable for me to assign, maybe as a test question or a final exam question, but probably more likely a homework type question because it's that tough to do.
Okay,
I have a
Professor.
question.
Oh,
Okay.
go ahead.
I just saw someone about a homework chatted that the program said it didn't do a homework. I do. Because okay, if you didn't get your assignment done, or if you got your assignment done and then your free trial elapsed, then it locks everything up until you pay. But once you pay for the account, basically the MyLab and mastering account, it should show everything else. It wouldn't hurt if you had taken or do take a snapshot of the grade. Also, sometimes it takes 24 hours for a change that you made there to appear in my grade book. So yeah, if you see it on your gradebook side, on the mastering side, it'll eventually get here. Don't worry too much about it, because at the end of the semester, I actually download it straight from the Pearson side, because I've discovered in the past that not everything transfers at the right time. So I always throw in the actual Pearson homework as opposed to just using it using my grade book. Anybody else? Somebody was asking something when I started reading these chats.
Yeah, I had a question. So I got an email at 6 a.m. this morning saying that I had a grade changed for my Physics 241 course for a random homework.
Okay, well, that might have been the automatic updating of a homework or something like that. I didn't do anything special in terms of grading. I'm still working on labs, for instance, but that would show up as a 241 lab grade. But if mastering went and updated latest homework assignment, and then that would report it.
Well, it was for my 241 class, which I took like a year ago.
Oh, okay.
So
Well, that's weird.
yeah, I didn't know. And it said you had changed it too, but I didn't have you for 241. So I just wasn't sure what was going on.
That's weird. Who's this talking?
Aiden Clavercamp.
Okay. Yeah. I never had you before. That's weird. I wonder. Yeah, I don't know what that is. I will look into that with my TCC help desk people. Check your transcripts too. I mean, the next time you have to send your transcript somewhere, make sure you check nothing's changed for the worse. They might have discovered we had some problems with some labs last semester that someone was teaching, and I'd made some executive decisions about giving students a better lab grade than they had actually gotten. So it could have been that, and it just took this long to implement, but that's the only thing I could think of.
It was just like a random mastering homework assignment.
Oh, was that? Okay, yeah.
So I don't know, but I just figured I'd ask.
Well, I actually got 2 emails last night about posting Physics 202 videos to my YouTube channel. I'm like, I don't have any 202 videos on my YouTube channel. I have a lot that are equivalent to 202, but I haven't taught a 202 since I started doing YouTube. So yeah, it's a weird world we live in.
Yep.
Only other thing that I have for you, Professor, is that I saw it in the chat and it reminded me, is that the lab that's due today on Canvas says it was due on the 7th. The due date was not pushed back.
Okay, I will fix that. And actually, I sent out an email for those of you who have lab all this week. I've tried to send out an email to everybody and tell them in class that we're not having lab this week. Obviously, the 241 class was this morning, so they'd know, but you're 242. We're not having lab this week, and the actual lab I'm going to give you till midnight tonight to turn in instead of the normal 1 o'clock or whatever we do.
Okay. I just wanted to let you know that on Canvas it says it was due on the 7th.
Okay, thanks. I'll correct that. So
wait.
Go ahead.
You just said that we're not having lab this week, and by what's due by midnight is what we had last week?
Yeah.
Okay.
Yeah, I'm just giving you extra time since we're not actually meeting. If you need help, I mean, still text me or whatever you need to do, and I can help you. But I just want to give you that extra time since we're not physically meeting. I'm going to use that time later for you're going to use that time later for the mother of all labs, which is basically a lab with an intense error propagation analysis that has to be done, and it can take a while if you didn't learn the material very well. It takes a long time to figure out what you're doing. So I'm giving you this time off to do whatever you want, and later on I'm going to steal that time back from you by assigning a lab. Okay. All right. Well, let's get started, folks.
I have a question as well.
Go ahead, William.
I joined a little bit later, so I just wanted to verify when we're doing the midterm.
We've moved it to Tuesday for this class.
Okay. Is there any specific time?
Yeah, during regular class time. So you either have to start at 45 minutes before class starts, which would be as early as 10:15, and that'll give you the full 2 hours, or you've got to start no later than right on time and finish it 45 minutes late, because I'm giving you 2 hours. Honestly, you shouldn't need 2 hours. Most people don't take it, but if you're wanting your full 2 hours, you have to show up between 10:15 and 11 a.m. to get that 2 hours in.
Okay, I just wanted to verify.
And just to confirm, there's no class on Tuesday. It's just the exam, and that's the lockdown.
Exactly. That's the whole thing. The whole kit and caboodle. All right, let's go ahead and get started on a problem here. One we hadn't done was actually one your book does early in the semester. I mean, early in the chapter. So I'm going to jump right in that and do a problem where you have 2 wires parallel to each other. And you know that, for instance, one wire, if it's got a current, say, going up, then that's going to create a magnetic field. You can stick your thumb in the direction of the current and wrap your fingers around. So that's going to make a magnetic field wrapping around this way, right? So it points towards you over here, right? And then it points this way in front, and then it points towards me over here, and then it points this way in the back. So if you go over to here, you see that at that point, the magnetic field is pointing that way. So now you've got a magnetic field this way, and you've got positive charges. If this current is also going up, you've got positive charges this way. So QV is that way, B is that way, and you get a magnetic field, I mean, a force that results in pulling the wires together. So two parallel currents are going to attract one another, whereas two anti-parallel currents are going to repel one another. I'm going to do that calculation, and technically you have to get a force per unit length, not just a straight force. So let me show you how to do that. So we basically have two wires. So two current carrying wires. With parallel currents. Is the force on them repulsive or attractive? And how big is it? Okay, so how big is the force? So what I'm drawing here is a current carrying wire with a current going upward. And then what I'm drawing next to it is a current carrying wire with a current also upward. This is going to be called I1. This is going to be called I2. Okay, and I'm going to say the distance between them, center to center, is D. Okay, so first thing I want to calculate is the magnetic field on 2 due to 1. Or let's say answer. The B field on 2 due to 1 is B to 1 is equal to, now we know basically right hand rule, put thumb in the direction of the current, curl around, you see that it's clearly going into the page here. So the magnetic field here is in this direction, actually in this direction, into the page. Okay, and that magnetic field is given by, we did it before with Ampere's law, mu 0 I1 over 2 pi times the distance between them. And technically it's, like I said, in the page. You could set up a coordinate system, for instance, where the z-axis is along the wire, and then say the x-axis is this way, and the y-axis, of course, would be into the page, and then we would just call it theta hat, and that would be wonderful. Okay, that works, but it's not that necessary here. Just drawing it, you know what direction it is. Okay, now what we need to do is calculate the force. So what is the force on 2 due to B to 1? So for that, we know that F is equal to I, or DF is equal to I DL cross B, where DL is a vector that runs along the wire in the same direction as the current. So I is upwards, and DL is also upwards. So DL cross B means I've got to adjust my fingers somewhere where this can be like the axle, this can be the current carrying wire I2. All of those different ways I can turn my hand are acceptable, but I have to stop and figure out which way am I allowed to curl my fingers downward. When I do that, I say, okay, well, I can't curl them into the page this way, but if I turn over like this, then I can curl them into the page this way. So I know that's the right orientation. And now I see my right thumb is just pointing to the left. So ultimately I get the force acting this way. Okay. So they're actually perpendicular to one another. So the cross product's really not that irrelevant. And ultimately what you just get is F on 2 due to 1 is just equal to, again, I'm saying with our coordinate system that I worked out, I'm sort of treating this as the positive x-axis. This is the positive y-axis going into the board. And this is the positive z-axis, okay? So in this case, if I actually wanted to write a vector, I'm now going to have to take I2 times the length of the wire times B21. So ultimately, I'm going to get mu 0 I1 I2 over 2 pi d. That's my I2 and that's my B. I still need my length, so I'm going to put an L there, and I'm going to say it's to the right, so it's in the J hat, or excuse me, it's to the left, so it's in the negative I hat direction. Okay. Normally, what you'd say is the force per unit length F21 over L is equal to negative mu 0 I1 I2 over 2 pi d. Whoa. Don't know how that happened. I said the word D when I was going to write 2, and my brain said, okay, that's what I'm going to write. 2 pi d I hat. So that's the crux of it. So what we've learned now is that parallel wires attract one another, parallel currents attract one another, and anti-parallel repel. So parallel currents attract, anti-parallel repel. Okay. And you can see that obviously if your QV was this way, then I'd have to point my hand down that way, which my arm don't bend that far, but you can see the force now is pointing that way. Okay. You could also do it with thinking about the individual charges. You just got to remember when we talk about current, we're pretending it's conventional current, which is positive charges going that way. So you could also use F equals QV cross B, which was the description I gave you before I actually drew the drawing. So we see the magnetic fields going into the page. Positive currents or positive charges are going up. That's what we pretend current is. So I do like this with my QV cross B, that gives me an F that way. So that says positive charges should tend to accumulate over here on this side. Okay. Any questions on that? Again, we're running into the Hall effect there, though, so you could actually use that to determine whether it's positive charges moving one way or negative charges moving the other. Deshaun asked about the midterm date, and I just want to make sure he heard me when I said it was Tuesday. Any questions on that, everybody? Okay, so this next problem is quite long, so I'm not going to try to fit it in on this one little page. And when I submit the notes, I'll cut it down to basically this big a piece of paper. So it won't really cause me any problems from a data standpoint. So let's get started on example 2. And this is one of those tough problems. It's one that's a little bigger than what you normally expect from a textbook example. Okay, so this is going to be example 2. And I'm going to say it out loud so you can hear it in the video or whatever. But the main thing is I'm going to draw it, and that's where you're going to get your information. So basically what we're going to have to do is we're going to imagine there exists a current carrying wire. Okay. And it's infinitely long. So we have an infinitely long current carrying wire. I'm going to imagine that's my x-axis. That's my y-axis. And then my z-axis is coming out of the page like that. That's the scenario I'm considering. So everybody hopefully can make sense of that three-dimensional drawing. And I'm actually looking for something to draw a neat circle, but it looks like I don't have it here with me. So I'll clean up the room recently, and all heck's broken loose now. All right, so what I'm going to do is I'm going to imagine there is a wire. So I'll just sort of do it like this just to try to make a circle. I'm going to imagine a circular wire right here that runs straight along the z-axis and in fact goes on for infinity. both towards and away from us. Okay. I'm going to say the radius of that wire is going to be RA. Okay. I'm also going to say that the current density, by the way, this wire is going to have a current coming out of the page. So the current will actually be coming out of the page, and that current is going to be called IA. So we could use a number if we want, but I'm just doing it all in symbols so we'll get a nice general result. But we're going to have to do some work. We're going to pretend we know IA, so that's why I labeled it here. We're going to pretend we know RA. However, we're going to have J, the current density, which we learned about in our earlier chapter. J is in fact going to be some constant K sub A. So you won't confuse it with the K from Coulomb's law or the K from the K hat vector times R cubed, where R is the cylindrical coordinate R. So it's basically just in the XY plane. It's X squared plus Y squared times the square root of X squared plus Y squared is what that R is. Now, because it's coming out of the page, that's in the K hat direction. And now it makes sense why I actually wrote KA. Okay. So part A, I would like to know what are the units of K? And what is K? Okay, so that's the first part. Part B, I'm going to try to figure out what is B for R less than RA. And part C, I'm going to try to figure out what is B for R greater than RA. So there's my parts. Okay. So let's get cracking on part A. Part A, I can see that J, unit-wise, has units of current per area. So that is amps per square meter. But J is also equal to KA R to the third. So that means KA has units of J over L cubed. So I can see now that's amps per square meter here divided by cubic meters. So I get amps per meter to the fifth. And that's what my units are for the K. And that's a useful thing to think about. If someone gives you this kind of thing, you need to be able to think about it, because when you're ultimately going to compute what K is, you've got to make sure that the units work out such that the current actually has units of amps. So that's important. So the other part of this that we're going to work is what is K? So I know that IA is equal to the integral of J dot dA. That's how we define the J current density initially. So I'm going to take J, which is KA R cubed, K hat, and I'm going to dot that with dA. Now, what's my dA? Well, it's kind of hard to show on this, so I'll look at just the end, say, of the wire. A little bigger, maybe. So that's supposed to be a circle. That's RA. What I'm going to do is I'm going to actually consider a circle of radius R that makes a washer whose thickness is dr. So this distance right here is dr. So 2 pi r is the distance around. If I were to cut this, it would almost make a perfect rectangle. If I sliced it and laid it out flat, it'd almost make a perfect rectangle. But in fact, it'd make more like a shape like this. But you can see on my YouTube channel, I'll work out the details of how much that differs from this. And it turns out it only differs by terms that are square or cubic and stuff like that in dr. So it's irrelevant. So what I can do is just call that 2 pi r dr. So I'm going to say the dA is 2 pi r dr, and it's supposed to point in the same direction as the current. So that's a k hat direction as well. Okay, and I don't know why I did two different colors on the same integral, but anyways. Now this is easy peasy because all I have to do is pull out all the constants, which is 2 pi k sub a. And now I'm going to integrate. Notice the k hat dot k hat just becomes 1, and I'm going to get r cubed dr. Excuse me, r to the 4th dr. The r cubed was already there, but I have an r that I had to take into account. So it's r 4th dr. And that's going to be an integral from 0 to r a. Because I need the whole current. And if I only did it out to some r, for instance, then that would be a part of the current. So ultimately what I'm going to get is 2/5 pi Ka Ra to the 5th is the current. So now I can solve for Ka, and I'd see that Ka is in fact equal to, let's say 5 Ia over 2 pi Ra to the 5th power. Notice that's completely consistent with the units we had. We had amps per meter to the 5th power. That's exactly what that is. Any questions on that? So this is also an answer to part A. Now we're going to use Ampere's law to calculate B, the magnetic field, for R less than RA. So I'm going to say B, R less than RA. And I'm going to do left-hand side of Ampere's law. Left-hand side of Ampere's law is the closed integral of B dot dl. And now what I'm going to do is I'm going to, again, imagine the end of that wire with actually some length to it. And my dl, of course, I don't know why I forgot my dl vector on there. My dl is going to be basically a concentric circle about the center whose radius is r, and therefore dl is going to be r d theta, because this would be d theta, and it's going to point in the theta hat direction. I know that's really small. Let me do it this way. Well, this angle here is d theta. Maybe that'll help. Yeah, it's not erasing very good, but anyways, I think you get it. Okay, so that's that. And then of course the arc length would be r d theta. And obviously this d theta is supposed to be really, really small, so it won't be that far off of that. But it does point in the theta hat direction, because remember, theta goes clockwise from the positive x-axis. So it's actually going that way, which is exactly the direction of the magnetic field. And I'm going to hypothesize, of course, that here's my hypothesis, is that B is equal to a function of R, but it's going to point in the theta hat direction. My job is to figure out what that B of R is. So I'm going to write this as the integral of B of R theta hat dotted with R d theta, theta hat. Obviously the theta hat dot theta hat, they'll go out to the side and that'll just become 1. Since we're on a circle of radius r to complete this line integral, we need not integrate the r because the r is a constant. So I'm going to get b of r times the integral of d theta from theta equals 0 to 2 pi, which is our typical left-hand side of Ampere's law. It's basically 2 pi r times b of r. The right-hand side is quite a bit more complicated. So the right-hand side is actually mu 0 I enclosed. So what I need you guys to do is keep me honest. I keep dropping this mu 0 when I normally do this calculation. I don't want to do that because obviously that's going to mess something up at the end. But what I'm going to do is I'm going to say that's mu 0 times the integral of j dot dA. Okay. So that's going to be equal to mu 0 times the integral of Ka r cubed. And of course, we already said that was in the k hat direction. And that's going to be dotted with, again, I want to use my 2 pi r dr. So it's going to be 2 pi r dr. And that's also going to be in the k hat direction. So the k hat dot k hat will allow the 2 pi r dr and the ka r cubed can go out in front of that because of the linearness of these dot product. And I get k dot k, which is just 1. And in fact, I can now bring out all the constants. I now have mu 0 ka times 2 pi, and that should be it. Now I'm going to have the integral of r to the 4th dr, and that goes from 0 to r. Okay, so it's just like that integral we did before, except now I'm only going to r instead of ra. So I can see already this is going to be mu 0 times 2 pi ka times 1/5 r to the 5th. So if I set left-hand side equal to right-hand side, as we're used to doing with Ampere's law, make sure you ask me questions if y'all aren't getting this, folks. Then I'm going to have 2 pi rb of r is equal to mu 0 times 2 pi ka over 5 r to the 5th. You can see already something nice happens. This r over here cancels out with one of these, leaving a 4 there. You can also see that this 2 pi cancels out with this 2 pi. And what we'll get is b of r is equal to mu 0 ka over 5, and that's r to the 4th. But now we want to substitute back in a because we weren't given ka. We should return this answer in terms of what we were given, which was the ia and the ra and all that good stuff. So now I'm going to go ahead and substitute in. I've got mu 0 over 5 times k, which we decided was 5 ia over 2 pi ra to the 5th. All of that times r to the 5th. And you can see a lot of nice cancellations here. Well, some nice cancellations. This 5 goes out with that. Actually, that's the only calculation. So it's not a lot of calculations. It's not a lot of cancellations. So the answer ultimately is B, the vector, is equal to mu 0 ia over 2 pi ra. Remember, that's just a constant to the 5th. And that's to the r to the 4th power. And all of this is in the theta hat direction. And this is for r less than ra. Any questions on that? So you can see that really is the quote unquote mother of all problems. This has all the stuff that I warned you I could do, which is I could take the J and have it some constant times some R to some power, or like in the case of Gauss's law, I could have used rho was equal to some constant times R cubed or something like that. And this is actually some reality in this, in that Oliver Heaviside argued, and I think Maxwell suspected it as well, but Oliver Heaviside realized quickly that when you were using an AC current going across the wire, basically all of the current was out here way along the outside edge, and the higher the frequency, the closer it got to the very edges of the wire. So modeling it as if most of it's way out here at the edge is a better reality in terms of what experimental evidence and Maxwell's equations show. Now, part C is super, super easy. So let's go ahead and do that, and then I'll do a nice little graph. So part C, I'm going to say left-hand side, which you might guess again. I'm just using the same hypothesis. B of R, B is equal to B of R theta hat. So B dot DL becomes the integral of B of R theta
Oh, we can't
hat.
see it.
Oh, thank you. B of R theta hat dotted with, now my DL is R d theta hat. Again, I'm using that same Amperian loop, if you will, right there. So since it's an Amperian loop of radius R, the R and the B of R are constant. So I get B of R times the integral of d theta from 0 to 2 pi. So this just becomes B of R times 2 pi R. The right-hand side is also easy. It's mu 0 I enclosed, which we already told you from the very beginning that the total current going through this wire is just IA. So that's just mu 0 IA. So B is just mu 0 IA over 2 pi R theta hat. And this is for R greater than RA. And if you notice, if you actually allow R to equal RA, what you get is RA to the 4th over RA to the 5th, which is 1 over RA times mu 0 I over 2 pi. And that's the exact same thing you get here. So you can actually add that equality symbol to it. And that's part C. Okay. Now, just for instructiveness, it's nice to actually look at what the plot of the magnetic field would be as a function of R. And I've got a nice big piece of paper here left, so I'm going to write it this way. 1, 2, 3, 4. Oh, this is nice. So I'll do this line right here. That's going to be mu 0 IA over 2 pi RA. So right there at that line, that's what's going to happen right at RA. And then I can cut RA in half, and this would be RA over 2. And then I can say twice RA would be here. And I could say 3 RA would be here. And I could say roughly 4 RA would be here. Reason why I do that is we see that first off, if you consider, let me make this a little cleaner since it turned out so ugly up here. This is going to be this point on the graph. That's the axis, and that's the magnetic field up there. If you notice the magnetic field for R less than RA, it goes like R to the 4th, right? So it actually ramps up really, it goes like R to the 4th, so it really ramps up really quickly. But if you take and calculate RA over 2, you see what's going to happen is I get basically 1/16 of RA to the 4th. So that's basically 1/16 as big as this. So if I divide this in 4s, this is 3/4, this is half, this is 1/4, this would be 1/8, this would be 1/16. So that's literally the first dot other than the 0 dot on this. So what happens is it goes from here through the spot and reaches that at RA. That's what that function looks like. Now, because we found this equality to hold that it's greater than or equal to and it's less than or equal to, then we know that the same spot's going to start with the other part of the curve, which is a 1 over R. Well, if I go to 1 over RA, then, or excuse me, if I go to R equals RA, then it's just that, which is exactly that. But if I go to 1/2 of that, R is equal to 2RA, say, then you see it's going to drop down to 1/2 of the value, which is right about here. And if I go down to 1/4 of the value, then it's going to drop down to 1/4, which would put it right about here. So you can see this function goes like 1 over R. So that's what the magnetic field of this wire looks like. While you're in the wire, it gets bigger and bigger and bigger, and you see the vast majority of the magnetic field is right at the surface, and then it falls off just like a regular wire at once you get outside of it. Any questions on that? So that is an actual example. Notice I didn't get any numbers. I mean, that's the trivial part. If you want to apply numbers to it, you can go back and say, let's say IA is going to be 4 amps, and let's say R is going to be, let's say 3 millimeters. And then you can calculate what is actual K in terms of amps per meter to the 5th power and all that stuff. So that's all fair game. It's just that's trivial application of arithmetic. So I work out the hard mathematical stuff so that you can just go back and apply numbers if you want to. I'm going to make this a little cleaner too. So that's for RA, and that's just plain R. There you go. So any questions on that before I move on? All right, so that's example 2, which I loved, by the way. Okay. And now I'm going to do example 3, which again, I'm actually building up to a more complex problem that I'm trying to solve. And this more complex problem is actually where I'm going to now introduce a magnetic field, or excuse me, introduce a current carrying wire that is hollow. So it's going to be a cylindrical shell, if you will. So this will be example 3. And what I'm going to do is introduce a hollow wire. And actually, let me draw it way over here. I looked for a circle I could use, but I couldn't find one. Anyways, and it's going to have an outer circle. That's the outer edge of the wire. Like this. Okay, and the z-axis is going to go right along here. And then I'm going to say this is the x-axis. And this is the y-axis. This is our z-axis. And then this wire is going to go on for infinity. Which really just means as long as you're about 10, preferably 100 times larger than the distances you're considering, then that's close enough. Okay, so that's really what this is. And again, I want to have J being equal to not Ka, but Kb R cubed. And of course, it's going to point in this case, I'm going to have the current going into the page. So I'm going to say the total current going into this wire is IB. I'm going to say this radius is RB. And I'm going to say this radius is RC. So this J is going to have to point into the plane. So I'm going to put a negative K K hat. Okay. So part A, I would like to know KB is question mark. Part B, I'd like to know B for, I think you can tell it's obvious with this configuration that the magnetic field inside is completely zero because there's no current enclosed inside of there. So I'm just jumping right to RB being less than R being less than RC. And then part C, I'm going to ask for B for R greater than RC. So that's what I'm shooting for. Does that make sense to everyone? All right, so let's do part A. I'm going to do a blue solution since I wrote the question in black. Does this bother anyone in this class, like seeing this? Because I've heard, you know, we have ADA rules and like I'm not allowed to put my syllabus in different colors, even though I always do by accident. Is this bothering anyone showing these different colors?
No, it's fine.
Okay, just let me know if any of y'all feel that way and I will change it. But I think it's better to sort of mix it up a little bit. So what I know is that IB is equal to the integral of J dot dA. I'm going to use everything like I did before. So my J this time, however, is going to be negative KB instead of KA. And it's going to be R cubed K hat. That's going to be having a dot product with, again, 2 pi R dr. That's also pointing in the same direction of the current. So I have to put a negative K hat on it. So I think you can see where I'm going with this. I'm just going to get 2 pi KB times the negatives cancel out. The K hat dot K hat becomes 1. I get integral of R to the 4th dr from R B to RC. That's the big difference here. So now we're going to get something ugly. We're going to have actually two terms, in other words. So now with this, I get 2 pi KB times RC to the 5th minus RB to the 5th. So that tells me KB should actually be equal to, I will say IB, put that in the middle. And then I'm going to divide by 2 pi because of that 2 pi. And then I'm going to divide by RC to the 5th minus RB to the 5th in parentheses. And that should be it. You can see that this again has units of amps per meter to the 5th. So that's just like the previous one, as we expected it should be. So this is the answer to part A. So we now know the current density and the coefficient in the current density. Now I don't know why I labeled that part B. That was supposed to be part A. I've been drinking watermelon. All right, here goes B. All right, so B is we want to know the magnetic field in between. So in this case, I'm going to take a nice Amperian loop, but instead of going around this way, I want my B dot DL to give me a positive value. So I need to go in the same direction as the current produces a magnetic field. So this current going this way, if you grabbed it with your right hand, it's actually going into the page, remember? So if you grabbed it with your right hand, you'd see it actually be going around in the negative theta hat direction. So I'm going to do the same thing and say this is the direction that it's going in. And in fact, this right here is DL, which should be R d theta, theta hat negative. So this little angle right here is d theta again. And of course, this radius is just plain R. So left-hand side of Ampere's law, the closed integral B dot dl? Well, my hypothesis again, B is equal to some B of R times negative theta hat. So there's my hypothesis. It's got the negative right in there in it, okay? I just want to make sure y'all see that that's actually a negative. So this is going to be integral B of R with a negative in front of it, theta hat, dotted with DL, which is negative R d theta, theta hat. Those two negatives are going to cancel out. And of course, theta hat dot theta hat is going to give us 1, and all the other junk can go out in front. And we're going to get our normal B of R times 2 pi R, because we're really integrating from theta equals 0 to 2 pi. Everybody kosher with that? Again, the ugly part is the right-hand side. So now I'll say the right-hand side, mu 0, I enclosed. Again, I'm going to try to keep remembering to write my mu 0, so catch me if I screw up. It's going to be mu 0 times the integral of J dot dA, and that's going to go from RC, or excuse me, RB to R, because we're not going all the way out to RC. We're doing a partial current. So we're going to say mu 0 times the integral. And of course, our J is just going to be like it was before. It's going to be K sub B, though, R cubed. And it's actually pointing in the negative K hat direction, because the current's going into the page. So I'll put the negative there. Then I'll put my dot product here. And again, I'm going to use the same area element, which is that little radius, or that little washer whose inner radius is R, and therefore its inner circumference is 2 pi R, and then I'm going to multiply that by dr. So that's going to be, of course, in the negative direction as well. So it's going to be negative 2 pi R dr in the k hat direction. And again, that's because the A is supposed to point along the direction of the K, so I had to put a negative on that as well. So all of this is pretty straightforward, and I get mu 0 times 2 pi KB equals, or times the integral of R to the 4th dr from RB to R, which equals mu 0 2 pi KB R to the 4th minus RB to the, or excuse me, R to the 5th. And it'll be a 5 over here. RB to the 5th. Okay. So now I should go ahead and substitute that KB in here that we already calculated. So I'm going to say it's equal to mu 0 times 2 pi over 5 times R to the 5th minus RB to the 5th. Now the KB we found was IB over 2 pi RC to the 5th minus RB to the 5th. So now when I do that, I can see a nice little 2 pi canceling out with a 2 pi, and that's pretty much it. So ultimately the current, or excuse me, the right-hand side is going to be mu 0 IB over 5 RC to the 5th minus RB to the 5th times R to the 5th minus RB to the 5th, like that. So now I've got it just in terms of stuff I know. I can set the left-hand side equal to the right-hand side. And when I do this, I get 2 pi R B of R is equal to mu 0 IB R to the 5th minus RB to the 5th over 5 RC to the 5th minus RB to the 5th. And that looks about like it. So I can now say, I'm going to pull this 2 pi back over here, and the R is going to go in the bottom. So I can now say that B, remember we hypothesized that it'd be negative B of R theta hat. So I'm going to put that negative in there and just call it mu 0 I B over this part. I should probably write, let's say 10 pi R times R C to the 5th minus RB to the 5th times R to the 5th minus RB to the 5th theta hat. And this is for R in between RB and RC. And is that part B or part C? That is part, no, that's part B. Really having a problem with my alphabet today. Crazy rule anyways. Whoever thought A was before B was before C. All right, everybody get how I got all that? Now the part C is really the easy one, and that's because we know the total current enclosed, so I ain't got to do all this crazy integral stuff. But what you're going to get is for part C, this is for R greater than RC. So the left-hand side, again, we're making the hypothesis that B is equal to negative B of R theta hat, and the integral B dot DL becomes integral B negative B of R theta hat dotted with negative R d theta hat. Again, we're using the same Amperian loop. So I just get positive B of R times 2 pi R. The right-hand side is super easy. In this case, get mu 0 I enclosed is just equal to mu 0 IB. So my answer is B is equal to negative mu 0 I B over 2 pi R theta hat for R greater than RC. And I'll circle this like this and say that's part C. And if you actually try to let R equal RC, when you do that here, you get RC minus RB to the 5th over RC minus RB to the 5th over RB. Lo and behold, you get exactly the same thing. But that 5 is still in there. Is that 5 supposed to be there? Was I supposed to cancel that out somewhere? I don't see anywhere for it to cancel out. What was my K? Did my K have a 5 in it that it was supposed to have? Aha. I forgot my 5 in here. That's why that stupid 5 showed up. Everybody see that? So let me correct that right now. So this should be instead 10 times pi. And then when I plug this in down here, sorry about this making the connections. I was hoping somebody might catch me if I did something stupid like that. What's worse is I actually worked it before and got it right. See, I did it to prep for class. But anyways, I still made the same mistake. Okay, or I still made a mistake. So now what you see is that actually that that doesn't become 10. That's just 2 pi. And that 2 pi cancels out with this 2 pi. Or does it? Let's see. That is the K, and the K was supposed to be 10 pi. Yeah, I was right the first time. Dang it. Or the second time, actually. So that 10 pi is going to cancel out with this 2 pi. Is that right? So IB, this becomes 10 pi down here. Let's make sure that's right with this. When oh no, the 2 pi's do, the 2 pi's do not cancel out. We'll still get, was supposed to be a 2 on top though? Maybe that's what happened. When I solve for KB, I should get 2 pi. That's what it was. The 5 should be in the top, not in the bottom. Dang it, man, it's so hard to track down an error if you make it. So this 2 pi is actually going to be in the bottom. But what we're missing is not a 10 pi, we're missing a 5 up top. Okay, so when I plug it in down here, I should have not had a 10 pi, I should have had a 2 pi, but I would have had a 5 up top. So I'll put this 5 here. I'll put this 2 pi back. I can see that the 2 pi's cancel out, but I can also see that the 5s cancel out. And that wouldn't be there at all. So I erase that, which means I shouldn't have this one either. So I don't have that 5 here. And that's going to make this just like I expected it to be, which was not 10 pi, but rather 2 pi. Okay, so now you see when R is equal to RC, I get RC to the 5th minus RB to the 5th over RC to the 5th minus RB to the 5th. And then this becomes RC as well. So I get mu 0 I over 2 pi RC, which is exactly what this is. So now I can add this and this here. Notice also if R is equal to RB, then that becomes 0. So I can put an equals on that as well. Well, even with that mistake and correcting it, I still managed to finish this with enough time to do the last part. If I really wanted to graph that, it'd be a lot more complicated because you see it doesn't just go like R or R cubed. In fact, for R between RB and RC, it goes like R to the 5th over R. Where's it at? Yeah, R to the 5th over R. So it's weighted a little bit, meaning it doesn't quite go like R to the 5th, R to the 4th, but it's somewhere close to that. And of course, it doesn't start at, well, it still starts at 0, but it's going to be like a different type function. So anyways, you could make that graph versus R, and that would be great, but no big deal right now. So that's that's example 3. Now I'm going to do the last part, which is example 4. And this one I think you'll find is really easy. So example 4. Let's imagine now that I have one wire, let's say right here, with a radius R sub A. Then outside of that, is a concentric cylindrical wire with inner radius RB and outer radius RC. Okay. And I'm going to draw my coordinate axis, my Z coordinate, as if it's coming out of the page, and it'll be coming just like this. So there's my Z axis. And then right here is my X axis. Right here is my Y axis. And I will show you that this goes on for infinity. And this too goes on for infinity. And its inner one, of course, goes on for infinity as well, as does this. Okay. So now what I'd like to know is what is the magnetic fields all over the place. So in this case, I'm going to say right here, I have a current coming out that is IA. And right here, I have a current going in that is IB. So you can see what I've done is just basically reconstructed all the other parts. And obviously, when you're dealing with all this, this is just example 2. When you're dealing with in between here, that's just example 2 as well, but part C. And then when you're in here, you're talking about example 3. And then when you get out here, you're part C of example 3. But notice now all I have left to do is calculate the electric or the magnetic field outside of this. So I want to know B for R less than RA. That's part A. Part B is B for R greater than RA. And part C is B for RB is less than RC. Part D is B for R greater than RC. Okay. Well, I can just go back through and compile basically everything I've already done. And my answers will be as follows. So part A, we already know, remember this is the same scenario, J equals KA, J sub A equals KA, R cubed, and JB equals KB times R cubed. So we have all those things that were going on before. So that's where all this stuff is coming from. But in the very first case, we found that 1 KA was equal to 5 IA over 2 pi RA to the 5th. And we found that B is equal to, for R smaller than RB, we found it's equal to mu 0 IA over 2 pi RA to the 5th times R to the 4th theta hat, and this is for R less than RA. For part B, we found that in between the two, that B is equal to mu 0 IA over 2 pi R theta hat again. And this is for R A is smaller than R is smaller than RB. But again, we were able to go back and make the equality true because when we plugged in the RA, that was right as well. Part C, we've already done as well. Part C was, first off, we found that KB was equal to, this is where I got to make sure I copy the right version instead of the crap version. And the right version was 5IB over 2 pi RC to the fifth minus RB to the fifth. And B turned out to be negative mu 0 IB times R to the fifth minus RB to the fifth over 2 pi R times RC to the fifth minus RB to the fifth theta hat. Now here's the problem. That was what we were found before, but remember we found that as if the only current inside was the current due to this outer ring. We can't do that anymore. So we've actually got to take into account that other one. So in this case, we know what that was, but now we got to say, okay, for R, B is less than R is less than RC, the left-hand side of Gauss's law, or excuse me, the Ampere's law, closed integral B dot dl is just equal to, again, B of R times 2 pi R. That's what it's always going to be, right? We just did the same old stuff we always do, all that good stuff. So the right-hand side is a little different, though. The right-hand side is going to be mu 0 I enclosed, which oddly enough is mu 0 times the I enclosed we got on the previous problem, which was, I'm stealing my previous problem, I enclosed. I found that to be basically what's going to happen is this, there's a magnetic field that's going to exist going around this way due to the inner wire. So that's going to be IA. But since we're integrating around that way, that's going to give you a negative of what we got for IB enclosed, I mean, for the enclosed current on the outer part of the wire. So I'm going to put a negative in front of that. And now I'm going to put the actual I enclosed for that particular R, which in this case was IB R to the fifth minus RB to the fifth over, here's got where I got to make sure I did it right. Over, I think this one was supposed to be just plain RC to the fifth minus RB to the fifth. So that looks right to me, assuming I didn't make any mistakes on my IB. So what I'm trying to use here is that. Remember that expression that we got, but we had those other problems. So this should actually be what it is. And now all that's equal to B0, or excuse me, all that's equal to B of R times 2 pi R. So now we say left-hand side equals right-hand side, and it gets a little odd, right? So we get, when we say this, we say B of R times 2 pi R is equal to mu 0 IA minus IB R to the 5th minus RB to the 5th over RC. I shouldn't have made that C that big. Over RC to the 5th minus RB to the 5th. So you can now say, oh, wow, this B of R is a lot more complicated. B is equal to mu 0 IA minus IB R to the 5th minus RB to the 5th over RC to the 5th minus RB to the 5th over 2 pi R, and in the theta hat direction. Because the theta hat direction was the positive one. If I had done the other way, it would be, I'd reverse this and put a negative on it, but you know, why would we do that anyways? So this is the full magnetic field now for RB is less than R is less than RC. And you can see as R approaches RC, this is just going to become IA minus IB. But if IA and IB are equal to each other, that's ultimately going to be 0, which brings us finally to part D. And that's, we're actually about 4 minutes late. You guys are free to go. I'm going to go ahead and finish this out. But obviously your time's up, but we don't have lab today. So, oh yeah. So we don't have lab today. So maybe you can just afford this extra few minutes. So the final part with this, we're going to have left-hand side of Gauss's law, of Ampere's law, is closed integral B dot dl is equal to B of R times 2 pi R. Again, making the hypothesis that in this case, B is going to be B of R times theta hat. Then the right-hand side just becomes mu 0 I enclosed, which is actually equal to mu 0 IA minus IB. So ultimately, B is going to be mu 0 IA minus IB over 2 pi R theta hat for R greater than R equal to RC. And that's part D. So we've now done this entirely big problem. Now the normal scenario is, does anybody know what kind of wire this is? What that's called? We mentioned it before, so I'm sure some of you do. It's what we use for DirecTV and Dish and cable.
Coaxial.
Yeah, coaxial. And the normal scenario is these currents are actually equal in magnitude, but opposite in direction. So you can see for a normal coaxial cable, since they're equal, that would just give you a 0 magnetic field outside. But this is the more general case. And that's it. That's sort of, you know, a major big deal problem to solve. That's, like I said, among the hardest that you get to solve in this level course. Hopefully that helps you understand how to do all this Ampere's law stuff. And we have now finished chapter 28. And I think chapter 28, if I'm not mistaken, chapter 28 conceptual questions are due Sunday and the actual problems are due Wednesday. Or excuse me, due Monday for you guys, because y'all are our Tuesday, Thursday class. So if anybody has any questions, you're free to stick around. Otherwise, you're free to go. Remember, there's no lab meeting today. Remember, you have until 11:59 p.m. tonight to complete, to turn in your lab from last week. And remember that sometime in the future, you might have to spend 2.5 to 5 hours on the mother of all propagation of error labs. So I will be available to help you with that to some extent. I'll introduce it to you. But then also you guys are free to work with each other, but you're each going to turn in your own report, and you should each do your best to learn the material completely, but by helping others. So thanks for coming, everybody.
And there's no class Tuesday because of the midterm.
Exactly. Thank you for reminding me of that. Yeah, the midterm is actually taken during the class. You can start as early as 10:15 since the class starts at 11, but you only have 2 hours no matter what time you start. And if you start after 11, you're actually going to get less than 2 hours because the test literally just disappears on you at, since we're supposed to be out at 12:15, it'll disappear at 1:15.
And I believe you said you would give us another chance at the lockdown midterm
Yeah,
as well.
I'm gonna open
or-
that back up and see what's wrong with it, open it back up and give y'all till Sunday night, Saturday night, I guess.
Thank you.
No problem.
Thank you, Professor. Have a good weekend.
You too.
Professor,
Yes,
just so I got this right, you did say there's no lab today, right?
that's correct.
Okay, thank you.
No problem. See you.
Have a nice weekend, sir.
You too.
Thank you.
Christian, do you want to discuss your email or want me to look it up real quick?
Yeah, I was just gonna say, like, okay, so let me turn down this. No, yeah, so I have my chemistry one at 9 a.m. and it's like 3 hours long, and then I would like at least a break in between.
Yeah.
So can I do it around like 1?
Yeah, I will have to make a different test for you and I'll like put your name in it or something like that. And I'll let you do that one.
Okay, thank
Okay,
you.
no problem. See you, Christian. Jasmine, Kendrick, William, do you guys have anything?
Yeah, I want to
Um,
ask you a little more. Oh, Jasmine, you can
William.
go.
No, you're fine.
Are you sure?
Yeah, go ahead.
Thanks for being a gentleman.
So, sir, so I chatted with you a little earlier about the homework. I just want to like reiterate it real quick. I am going to go through. I'm going to try and get it all like done and get as high as a grade as I can. But I do I can swear by it that I did the homework and I don't know what happened.